Alright, welcome back. So here we have a statement, theorem 2.5, which we feel and we believe and we've seen is true. If we have a system of linear equations, we're either going to get one solution, infinitely many, or none. We know this is true for the 2x2 case, or the two-dimensional case, because you can just think about the ways that lines can intersect. They can intersect at one point, they can be the same line, or they can be parallel lines that are distinct. So let's go ahead and actually prove this, because that will allow us to verify it for more than 2x2 cases. Alright, so to begin the proof, what we're going to want to do is we're going to want to start by making some assumptions and defining our variables. So one thing that we might recall is that every linear system can be written in the form ax equals b. Okay, so let's go ahead and define our linear system that way. So consider a linear system. I guess I didn't give myself enough room, so we'll erase that. A linear system with matrix representation ax equals b. Alright, so then we have to think about what to do next. So the theorem itself says that three different possible things could happen. So we probably want to break our proof down into three possible different things. So if we think about it, the statements has 1, 0, or any other situation. Oh, I underlined those in the wrong order. 1, 0, or anything else. So we probably want to break our cases up in a similar way. So we will consider three cases. Either ax equals b has no solutions, exactly one solution, or if we think about what the other option is off of these two, the next thing you'd have is at least two solutions, or at least two solutions. Alright, so the first two cases are going to be super simple. So case 1, so assume ax equals b has no solutions. Well, then we're already done. We're already in C from the theorem. Then we want to start capital T. Then we are in case 3. Of the theorem. Alright, so let's similarly do case 2. Assume ax equals b has one solution. Exactly one solution. Well, then again, we're already done. We're already in case A. 1. So actually, let's fix this 3. See, we can always edit proofs. We can always go back, so we are in case C here. And in this case, then we are in case A of theorem 2.5. Okay, so lastly, our third case here, this is going to be the longer one because it doesn't follow immediately, right? We're having at least two solutions. We want at least two solutions to lead to infinitely many. So let's assume ax equals b has at least two solutions. Let's call these two solutions that we know we have U and V. And we'll remind ourselves, since we have two, U is not equal to V. All right. So what it means for them, so this means that they're solutions that A times U and A times V are both equal to B. Okay. So then, in fact, we can see that A times U minus V is equal to A times U minus A times V. And let's actually do this in a way where we say that this was distributivity. Matrix multiplication. Then we have that this A times U is B, A times V is B, so that would be substitution. And then B minus B is equal to the 0 matrix. All right, because we have an additive inverse. All right, so what can we do with this fact? Let's keep going. So, moreover, oh, we should put a period here. Moreover, U minus V is not equal to the 0 vector. Right? So now, so for every scalar, C, the n by 1 matrix, U plus C times U minus V is distinct. All right. Since we're not adding 0, we're always going to get something different. Okay. So let's then notice, again, we're trying to find infinitely many solutions to AX equals B. So I've just written down an infinite number of vectors here. So we notice that A times U plus C times U minus V, this infinite family of vectors I wrote down, we can use distributivity again, plus C A U minus V. Okay, so by distributivity, and I suppose we use dissociativity of scalars. Right. So AU we know is B. That's what we have way up here, underlined in pink, plus C. Oh look, we also have that A times U minus V is equal to 0. So C times 0. So this is entirely substitution. All right. But really, we just added 0, so B. All right. So we'll say that that's the additive identity. All right, so end of a sentence, we put our period. So therefore, we have written down infinitely many solutions to AX equals B. So we are in case B of theorem 2.5. All right, and we'll put our QED box to tell the reader that we've finished. All right, So again, we went through the three possible cases. Okay, either you have 0 solutions, 1 solution, or 2 or more solutions. And we showed that in each of these three cases, one of A, B, or C had to hold. Right. It is possible that we could have gone through these three cases and maybe 2 of them went to the same situation. That's totally a thing that you can do, but in this case, we didn't have to. Alright, that's it for this proof. Have a good one. Bye-bye.